EDD midterm presentation.
By Austin Rowland, Jack Hillman, Milan Patel, and Ethan Coleman.
Star problem. According to the World Health Organization, 785 million people suffer from poor access to drinkable water or to a service that provides it, and 2 billion may consume contaminated water. This especially affects poor individuals and those located in underdeveloped regions. Without a sufficient source of water, individuals are more likely to develop diseases and become malnourished. It also removes individuals from a working environment because time is needed for water, not to mention the violence when resources are lacking, and treating water can be an expensive option. According to the World Health Organization, the main problem is pollutants in the water. It's not actually like an access to water for the majority of things. So, and a lot of this is because of how regions are designed, mostly for economic gain, which prevents people from getting access to clean water. So why it's a problem? Clean drinkable water is a fundamental need for everyone, yet people, even in the United States, have an issue getting it at an affordable price because bottled water can be expensive and so can filters. I don't have any exact numbers on these, but if you buy a Brita filter, it can be pretty expensive. And also bottled water, if you're looking to get high quantities of it, especially in places where it's lacking, can be pretty expensive due to supply and demand. And reducing this issue could lead to healthier individuals because it's seen people who drink sufficient amounts of water are typically healthier and they're able to rid pollutants of their bodies. And this could have a huge effect on society.
All right, so our solution is going to be a 6-module system for the filtration of this water. As Coleman had stated in the last slide, we have to just get rid of the polluted water, the pollutants in the water. So to do so, as you can see in the first picture, there would be a small slot where water would be able to come in. The idea is that this machine will be put into a river and the flow of the water will help it go through the rest of the modules. So each of them are not going to be very big, but they're going to be able to store a good amount of water so it can go through the process and produce, hopefully at the end, a clean glass of water. So as you can see, each of the modules are labeled 1, 2, 3, 4, 5, and the final part, which is going to be dispensing that water.
All right, so in case you weren't listening to my man Milan, here are the 6 modules all summed up for you. So the first module is our intake module. So all that is an intake of water from the surroundings. And like Milan said, that flow is going to go through all the rest of the modules as well. So 2 is our transportation tube. This will move the water from the intake module to the next chamber in a manageable amount, which it needs to be manageable for our module 3, which is our filtration device, and that's within the transportation tube. It's removable and it will separate water from larger particles and debris. And once it is removed from the device, it can be cleaned and put back into the system. Module 4 is our UV light chamber, which harnesses UV light to eradicate biological threats and microorganisms. Module 5 is our desalinization module. So it is the intake of clean water. It removes salt via reversed osmosis, which, as you can see, there is extreme pressure through a semi-permeable membrane. And the pressurized water from reverse osmosis will hit a hydroelectric turbine and generate power used to sustain itself. And our last module is the collection unit, and this will collect the water in a removable unit.
So our current status with our project, we've come up with our problems and solutions and made progress with physical drawings and our solution models. Our daunting task is currently figuring out how to take the project to a physical standard as a product, and at the end of the course we'll be figuring out how to proceed with that digitally. And so possible outcomes we hope to obtain is a CAD model, and an issue we have with that is that only one member of our group has access to Inventor, so we will be working on that later on. So how we're working together. So like everyone else, we've been using Zoom, we've been texting. As you can see in this picture right here, we've all been communicating through online messages.
So our long-term goals are what we kind of started this project with. So when we were thinking of the problem, we thought, okay, what is clean water going to improve in places that don't have it? It's going to improve their basic needs, their health like requirements, which will have a sort of trickle down effect on things such as agricultural developments, ability to focus on education and economic improvement. And those will lead to things such as higher crop yield, more knowledgeable individuals in the area, and a higher budget and income that they can actually use. And all of those collectively come together for an area to form better opportunities and allow people in that area to have a greater global contribution.
So our motivation is the legend himself, the Mr. Masikis. As you can see, this is during quarantine, so the beard and everything is gone. But you should see him in class. That man is irresistible. But our motivation, he has helped us through this process. We wouldn't have gotten anywhere in this engineering capstone project without him, quite literally, because we wouldn't have gotten any work done. So we want to thank him for all he has done for us. And moving on.
We miss you, Seek.
Miss you. Thank you. El Fini.
Elfin. All right. Hit us in the D.